We're doing chapter 5, which is all about resampling methods using these, at least till yesterday, cross-validation approaches, where we had, what was it? Leave one out, cross-validation, and k-fold, cross-validation. We're moving on to the second section of this book, within this chapter, naturally, where we're going to discuss the bootstrap. Let's begin. The bootstrap is a widely applicable and extremely powerful statistical tool that can be used to quantify the uncertainty associated with a given estimator or statistical learning method. So we're looking at uncertainty over here. As a simple example, the bootstrap can be used to estimate the standard errors of the coefficients from a linear regression fit. Do we remember these standard errors? If we quickly revisit chapter 3, we had invested quite some time in building an intuitive understanding of the standard error associated with B0 hat and the standard error for B1 hat. And we kind of got an idea in R as well when I'm doing the same thing I did yesterday, where in a session maybe 2-3 weeks ago, we had discussed each one of us going out and collecting 50 observations from the same or on 50 observations of the same type. So we're interviewing people, for example, and we're all going to have, or at least one would expect, that we will all have slightly different values for our beta naught and our beta 1. And these beta 1s are, at least for the data that I'm using over here, are these 50. And then you can calculate the standard error within these estimates. And what had I done? Let's see. We had this is the formula in the book. This is the formula. But you could just look at a box plot, right? You could just look at a box plot and you get an idea of the variability within the estimated beta 1 hats. So you have the least value is 1.59, quite the outlier next to the rest. Same goes for 2.35, but on the other side of the interval of values. And bootstrap is going to be maybe a more elegant way. No. The idea was that when calculating, so the formulae over here, let's find them. The formulae over here depend on the variability, the variance. Could also call it variability within the error term. Now you usually won't know the error term, so this is an approximation. And Bootstrap is probably going to do something similar, where you don't have the actual data, you don't have the actual sigma, but you can still approximate it. Let's see. So in the specific case of linear regression, this is not particularly useful, since we saw in chapter 3 that standard statistical software, such as R, outputs such standard errors automatically, right? So the standard error, do we have yesterday's code? So if I just run this entire thing, this was on the cars, on the auto data set. Does it, if we do summary for the last fit, which excludes the last observation, not that that's that important, but right. So if it's linear regression, there are these formulae that we just saw in chapter 3 that rely on sigma that quite easily calculate the standard error. I guess Bootstrap is going to be, or it's going to come into its own. We're going to find it useful when we're using models that perhaps do not depend on the assumption of linearity. Let's have a look. So in the specific case of linear regression, Bootstrap is not particularly useful, since we saw in chapter 3 that standard statistical software, so for example, R, when we use LM, outputs, such standard errors automatically. However, the power of the Bootstrap lies in the fact that it can be easily applied to a wide range of statistical learning methods, including some for which a measure of variability is otherwise difficult to obtain and is not automatically output by statistical software. In this section, we illustrate the Bootstrap on a toy example, meaning we're just looking at simulated data, in which we wish to determine the best investment allocation under a simple model. So I would imagine this might be qualitative data, it might be a classification model, because we're looking at best investment allocation, unless the numerical outputs are going to be, so we're going to invest in only 2 companies. Pick your favorite 2 companies. Let's see, 2 that are quoted on some major stock exchange. I'm trying to avoid the FANG companies. So if I avoid Facebook, Apple, Amazon, Netflix, and Google, what does that leave us with? It could be a gaming company like Roblox. We're probably too old to have ever really spent much of our lives on Roblox, but we could take Roblox. It's one extremely popular gaming company for the sort of the 5-year-olds to 15-year-olds age group, and another company could be, I don't know, like an airline company. So take, for instance, I don't know, British Airways. And I guess that could be a quantitative model where you're asking, if I have 1,000 euros to invest, what should be my percentage allocation? Should I go 90% in Roblox, the rest in British Airways, or similar? Let's have a look. So the best investment allocation under simple model in section 5.3, we explore the use of the Bootstrap to assess the variability associated with the regression coefficients in a linear model. Okay, so we're still going to look at these linear models where, even though in the first chapter we said it's not that useful, maybe just to see that we get the same results as what the software the software of our choice gives us when we run the code. Let's see. Oh yeah, it's I think quite similar to what I was expecting. Suppose that we wish to invest a fixed sum of money in 2 financial assets that yield returns of X and Y. So these are numerical variables, X and Y, and you can think of the return as being, for example, anywhere between, can you have a negative return? Well, yes, of course, right? It can't be less than negative 100%, but it can be as low as negative 100%, right? Where you have loss, where that stock becomes worthless. Think of I was going to say maybe Kodak, which companies have seen usually you get this like with Ponzi schemes, but that wouldn't be quite a financial asset. That would be you've you don't really have a backing asset over there. Where X and Y are random quantities. We will invest a fraction alpha of our money in X, in the X asset. Okay, so I think we're using X to mean two things. We're using X to represent the return on asset X. Ideally, perhaps we would have made a bit clearer, but as is often the case with these things, context is everything. So we will invest a fraction alpha of our money in asset X. So think of Roblox, and we'll invest the remaining 1 minus alpha in Y. Think of British Airways. Since there is variability associated with the returns on these two assets, we wish to choose alpha to minimize the total risk or variance of our investment. In other words, what do we want to minimize? So it's our total investment. So our total investment, or I don't really that yields returns of X and Y. So what is X? Is X? I think X is just the return, right, that we're going to make. So this is depending on the choice of alpha, and you could go all in to X, right? So if you take alpha of 1, you zeroize the second term. But for a choice of alpha, your total return is now a function of the return on investment X. So think of it as maybe you wouldn't really work in percentages, would you? Because adding percentages very often it leads to nonsensical answers. So just think of this as a monetary return. So you're measuring the euro return on asset X and the euro return on asset Y. And you want to check the variability. So most things in finance, and this goes way beyond finance, and in fact, you get this in like these debates. For example, let's not politicize the argument. It could be anything. It could be the current abortion debate that we're having in our own country. But you always have that person that kind of points out it's very difficult to separate politics from anything really. And the same thing with finance. So in finance and sort of by extension, in fact, there's the expression, it's the economy, comma, stupid. Because very, very often things boil down to pragmatic economic considerations. And what do we want as investors? What do we want? Well, you usually want to maximize your expected return while minimizing the risk. Now, it's very optimistic to if one believes that you can optimize both of them. But going into Desmos, I'll just make this clear. We'll look at a single variable, and we'll take our Gaussian bell-shaped probability density function, 1 over the square root of 2 pi sigma exp negative 1 all over, is it 2 sigma? And x minus mu parameter like this. I'll do this. So this is your, if the mean is 0, this is perhaps the most famous, the most celebrated probability density function. As always, if you take, since it's a curve, if you take the area, and I'll just approximate negative infinity and infinity with negative 100 and 100, if you take the area, that's exactly 1. So that's telling you the probability of getting some real number. You need to think of it as a histogram. The probability of getting some real number. So think of it as heads and tails. The probability of getting heads is 50%. The probability of getting tails is 50%. The probability of getting heads or tails, and you've exhausted the full set of possible outcomes, is 1. You have to get either heads or tails. We're saying the same thing over here with this integral. The probability of getting some, not heads or tails this time around, but some value between negative 100 and 100 is, well, that's an approximation. It's not exactly 1. A better approximation would be if I took from negative 1,000 to 1,000, and you can always make that approximation better, is 1. Now, the mean is 0. That's what you would expect. You can run it in R. You can run it in R over here. And what do we tell R? We just say just some sample values, R normal distribution. And if we, by the way, the great feature about using RStudio is that not only does it complete the sort of the line of code, if you will, but it also tells you if, or when specifying a function, these are probably too small for you to be able to make them out that clearly. But if there are any, think of them as default inputs. And the default parameters within R are a 0 mean and a standard deviation of 1. So I don't even, if I wish to use the standard normal, density, let's just call it the density. I don't even need to explicitly state that. I can just say 1,000 variables, 1,000 simulations, and if I calculate the mean, I'm going to get something relatively close to 0. In fact, it's negative 0.09. If I took 10,000, then that would be a better sort of, you taking more observations, and now it's closer to 0 by a whole order of magnitude. Now, what do you want as an investor? What do you want? Well, you want to maximize your expected return. You probably wouldn't be too happy to hear that the asset has an expected return of 0%. It could be worse, but you probably wouldn't be too satisfied with this investment. So maybe you're hoping for a return of, let's just think of it as euros, of maybe 5,000 euros. And you want to minimize the variance. You want, let's take it from 0 to 10, for instance, and you want something like this. So something like this, the probability, look, let me show you. What is the probability of getting between, for example, between 5 and 6? Like this is probability of 15%. But if I increase the standard deviation like this, now getting between 5 and 6, 1 second, that can't be right. How do I have this is greater than 1? 1 second, 1 second. Now either this is wrong. That's funny, isn't it? Shouldn't we have an area of 1? Maybe we shouldn't spend too much time on this, but let's take from... That's odd. Now it's either Desmos just isn't coping. Yeah, I think maybe it's trying to do some kind of Simpson's rule or trapezoidal rule. And although that would surprise me if it's not handling... It would surprise me quite a bit. What if I... Now that's fine. That's fine. So what if... So maybe it doesn't like it when we take a standard deviation less than 1 for whatever reason. Now that's actually quite worrying. I might have something wrong over here. Maybe there isn't an S. Can we just look it up? This is the normal. That S might be wrong. Normal distribution. And the S is actually has to be within the brackets. So I think we were getting lucky when we had S. When we had S1 wasn't really interfering with anything, but we need to square that. And now this remains 1, regardless of the parameters. Okay, so the idea is if you want to make between 5 and 6, let's say you want to make more than a probability. You want more than a probability of 7. Why is that 1? Because about 15. So let's say you're interested in making a probability of more than 15.5. So we have, if this is the distribution, if this is the probability distribution, the histogram, that's sort of governing the asset's investment performance, then with these parameters, you have a 10% chance of making a return that is greater than or equal to 15.5, but less than or equal to 20. Now, if you increase the variance, this is going to decrease. No, it's actually... Maybe I'm looking at it the wrong way. Yeah, because it is getting flatter, isn't it? Yeah, I think this is the wrong way of looking at the calculation is right. The calculation is right. But all I need us to understand, and I hope I haven't confused anyone over here, is that the smaller, let's forget about that probability calculation for the time being, but the smaller the lower the standard deviation, S, the sigma parameter, the more certain you are of the outcome. Now, finance is all about trying to maximize your expected outcome, your average outcome, while reducing the variance. So we want to reduce this variance. Now it turns out, and this is definitely a result that the book is not expecting us to derive. It's not too difficult, by the way. But to minimize, think of this as the risk. That's the risk. The book uses exactly the same language. This is the risk. The alpha that reduces the risk. So think of it as which alpha gives you the minimum of this variance is in fact obtained from this expression. Now, what do these things mean? Very, very simple. No, really. Let's use different colors. This is just the variance associated with the first investment, with the first asset's investment performance. So how volatile is the first investment? Is it something that's historically been extremely volatile? Think of Bitcoin, for instance. Or is it something a lot less volatile, like a government bond? Same thing with sigma y squared. And the final term that appears is what is known as the covariance of x comma y. Again, for the purposes of this book, just think of it as the variability within x and y. If they were totally independent of each other, if the way, and in finance, as with most things, there really are no two physical, real world examples that are entirely independent of each other. But if they were totally independent, this would be 0, if I remember my covariance. Otherwise, it varies depending on how one asset impacts the other asset. Now, continuing with the book, in reality, these 3 quantities are unknown. We can compute estimates for these quantities. So that's where we introduce the hats using a data set that contains past measurements for X and Y, right? So even just now I said Bitcoin has historically been extremely volatile relative to other currencies, if you want to think of Bitcoin as a currency. And the book is really using the same approach when it discusses the past measurements for X and Y. We can then estimate the value of alpha that minimizes the variance of our investment using, it's the same formula, isn't it? But it's all, it is an estimate output, which is a function of these estimated variances and covariance. And we're going to do this over here. And this is fun because it's like a finance example. Figure 5.9 illustrates this approach for estimating alpha on a simulated data set. In each panel, we simulated 100 pairs of returns for the investments X and Y. So in each panel, so we have 4 panels over here. And these are the returns. And by the way, you get these, you would expect, I think, a positive covariance, because they kind of, if you know something about X, it can give you an idea about Y. There tends to be this positive correlation between them. So we have 100. You can think of, for example, each point would be the return on a given day. So for example, this might be day 57, and Y didn't really change in terms of its value, but X went up by around 2. Don't ask me what these units are. We'll probably taking a unitless example. Okay. Now the idea is that you can perform it multiple times. I guess we're going to use this. So you calculate the variance for x. What does that mean? That means you only look at the x component for each observation. You only look at the x component for each observation. So you're just going to look at the x-axis, and you calculate the standard deviation. We do this in R. Maybe we open a new script. What should I type? I would like to type, let's say, for example, plot R norm 100 against R norm 100. There you go. So that's 100 observations. It looks like a lot less, right? But it should be 100 observations. If I just look at this, that's 100 of them, and the same goes for the other one. Yeah. Why don't we do them separately? So this is our x variable, our y variable, and now you can calculate the standard deviation. Is that the command? SD. Okay, so you have 1.08. The standard deviation of y. Again, expect something similar. Roughly 1. I use the standard normal deviation. Beg your pardon. I use the standard normal density function to generate these 100 x values and these 100 y values, and the plot is plotting all of them. And then there's the covariance. Now, how do you calculate the covariance in R? I'm embarrassed to say I have no idea. So I wonder if I type something like, yes. So that was a lucky guess. I must be honest. And you correlation, variance, and covariance. You need to give it. Can we just say x and y? Yeah, that seems to work. And you get roughly 0 over here, because I've taken these two as to be totally independent of each other. X and y, there is in no way does y influence x. What do I mean by that? So look, if you know the value of y, it really doesn't tell you anything about x. The data is telling you for this green value of y, x was this negative value, it was also this value, it was also this value. So the x is all over the place. Whereas in this book, if you know something about y, then the suggestion is, the data is suggesting that you can say that x is probably also going to be positive. So this is kind of positive correlation. If y is positive, then you're expecting x to be positive. On the other hand, if y is negative, again, the data suggests, and really that's all we can say without maybe a more first principles. Thing is, statistics is used a lot in medicine, for example. Usually the statistics aren't enough. Then you actually need to, you need to speak to the biologist, you need to speak to the pharmacist, and they'll tell you, oh, right, okay, yeah, your data does make sense, because now that you've shown us the way I don't know, the way the numbers are related, it's just occurred to us that we can give you a scientific isn't the right word because um, a medical explanation, because we know that the human body works this way and that way. So it that would then the statistics would then lead to maybe some kind of hypothesis about the human body or whatever. So contrary to what I'm doing in R, this book has, or this section has X and Y positively correlated. So that would be a non-zero covariance term. We used these returns to estimate these three values, just like I did in R, which we then substituted into 5.7 to estimate, or in order to obtain estimates for alpha. The value of alpha hat resulting from each simulated data set ranges from 0.532 to 0.657. So if you evaluate this expression for each of these four data sets, the great thing is that instead of calculating one alpha, we get sort of, these four are giving us, in many ways, they're giving us a confidence interval, aren't they? So they're telling us to one extreme, we would minimize our total risk by investing 53% of our assets in Roblox. On the other hand, they're saying actually maybe that could be as high as 65.7% of the portfolio allocation going towards the Roblox stock, which, by the way, has had a very, very bad 12 months. If you follow these things at all, we're talking easily 60% down the all-time high, which wasn't that long ago because it was only very recently gone public. It is natural to wish to quantify the accuracy, and this is the whole thing, right? The accuracy of our estimate of alpha. So we would like a standard deviation of alpha hat. And to estimate this, we repeat the process of simulating 100 paired observations of X and Y. It's a pity they don't give the code for these examples, and estimating alpha using 5.7 1,000 times. We thereby obtained 1,000 estimates for alpha. Can we do this very quickly in R? Let's see. So as is often the case, we have 4. We'll just call it I. We're going to mimic the book. So we'll take 1,000 of them. We'll do the null vector, and we'll call this alpha estimates, and we'll just assign null to it for the time being. We don't need to use I for every I iteration. As long as I don't set a seed, we will have a different. We will have 100 different X simulations and Y simulations. Then we need to calculate. Then we just need to calculate alpha, right? Let's call it alpha or alpha hat. And the formula is, you think I would know it from, by the way, you'll be using this formula. So when I sat the actuarial exams, it was CT8. And I think these days it's CS2. So we need this fraction, and it is as the y squared minus covariance like that. And then as the x squared plus as the, whoopsie, y squared minus 2 times this covariance. And we can delete the plot like this. Let me just double check everything. The standard deviation of y squared, that's the variance of y, minus the covariance of x and y, divided by the variance of x plus the variance of y minus 2 times the covariance of x and y. And final step like this. And for each iteration, extend this vector by the newly created. Now, is this a typo? If you type 4, yeah, I'm missing a bracket, aren't I, over there? And we'll say C just means concatenate, alpha estimates, comma, alpha hat, run this thing. Great. And I think that bracket came back to haunt us. It's just 4 I 1 in 1,000. Okay, I think I was missing this as well, right? So does this work now? Yep. And final thing, display all of them over here. Round. Ugh. Two decimal places. And these are our alphas. These are the alphas, okay? As you can see, since x and y are totally independent of each other, and they have the same parameters, a mean of 0 and a standard deviation of 1, the alpha allocation is just telling you, well, just put 50% in one asset and 50% in another asset. It really makes no difference. And we can calculate the mean of this, and that's, practically 50%. We can also calculate the standard deviation. That gives us an idea of the sort of the confidence that we have in this thing. Alpha, which is 0.05. So it's very, 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 very narrow. If you divide, what does very narrow mean? If you divide these two, you get an idea. We've been doing this quite a bit to calculate p-values as well. You calculate, when you divide the mean by the standard deviation, the mean is 10 times larger. It might actually make sense to swap these around. So your standard deviation is only 10%. Well, I say only 10% is actually, it could be considered high. So we thereby obtained 1,000 estimates for alpha, which we call alpha 1 hat until alpha 1,000 hat. The left-hand panel of figure 5.10 displays a histogram of the resulting estimates. So this is a histogram. Interesting, there are two colors. Maybe they're playing God in one of them, where they know the actual. The left-hand panel, yeah. For these simulations, the parameters. Okay. Can we maybe get something close to the book? For these simulations, the parameters were set to the standard deviation of x is 1, and the standard deviation, well, the variance of x is 1, and the variance of y is 2. Why am I saying 2? It's 1.25. And the covariance is 0.5. Now, the thing is, they're not telling us, they're giving us the variance, but they're not telling us what kind of probability distribution. Is it standard normal? Is it maybe just, well, I mean, it's obviously not standard normal. Standard normal would be if the variance was 1. So I'm not entirely sure I can quite replicate their data, but at least we can get maybe a bit closer to what they have. The question is how do you get the 0.5, or is there just a formula that's based on these two? It might be. Let's look at this with standard deviation of 1.25. And now we have a mean of 0.61. And, oh yeah, look, very close to what they have, right? Assuming that the pink represents the mean. The pink line indicates the true value of alpha. So yeah, how did they calculate the true value? They just used this formula. They just inputted 1, 1.25. Wait, no, mine is wrong. Mine is wrong because they said that the variance of y is 1.25, whereas I've taken it as the standard deviation. So I actually need to you need to square root the way our syntax works. If you're specifying a normal distribution, you don't give it the variance, you give it the standard deviation, which is a square root. So unfortunately, we now don't have 0.6, but we do have 0.55. So well, maybe the true value is 0.6, but just our simulations gave us 0.55. I think probably what ours has different to the book is this covariance. I could tell you what the covariance is for each 100x and 100y by creating a covariance estimates vector. And as always, we're using the same techniques, aren't we, very often? Covariance estimates, covariance estimates, and include the covariance of x and y. Let's see if we have anything close to their own covariance. Again, just an approximation, but it's interesting to have a look. No. So on average, my covariance is very, very, very different to the covariance. Yes, of course, because I took, because we were expecting practically 0, right? Whereas their covariance is positive. How could I create this? How could I create something? How could I take two random quantities, two random variables that have a positive covariance? I don't know is the answer, but they clearly haven't simulated their own data using just the normal, or at least I've taken practically identical normal distributions. The only difference is my second one doesn't have a standard deviation of 1. Okay. So for these simulations, the parameters, again, authors playing God, the parameters were set to these. So we know that the true value of alpha is 0.6. We can just evaluate that. We indicated this value using a solid vertical line on the histogram. Okay. Now, we're going to have to distinguish between the orange and blue. The mean over all 1,000 estimates for alpha is 0.5996. Very close to alpha equals 0.6. So this is using bootstrapping, by the way. And the standard deviation of the estimates, this is just a formula, you don't need to know it, but every time in R, we do the SD function, the standard deviation, to calculate the variability within a data set. It is this formula that's being calculated each time. Notice the square root. Without it, that would be the variance. This gives us a very good idea of the accuracy of alpha hat. The standard error of alpha hat is 0.083. So roughly speaking, from a random sample from the population, we would expect alpha hat. So if you had to pick a random sample, one of these 4, for instance. Now, of course, the authors have used 1,000, but if you had to pick one of these four from these 1,000 simulations, each of 100 data points, then you would expect that the alpha hat that it gives you differs from alpha by approximately 0.08 on average. Now, in practice, the procedure for estimating the standard error of alpha hat outlined above cannot be applied because for real data, we cannot generate new samples from the original population. Okay. So actually, did I say that this is Bootstrap? This is certainly not Bootstrap. This is not Bootstrap. This is your God. You know these sigmas, and you can ask R based on the sigmas, sigma of 1, sigma of square root of 1.25, etc., to generate 100, and then you ask it to do it again and to do it again 1,000 times, and then you take the mean. So in real life, and apologies, I did misspeak earlier. I said this is the Bootstrap. No, we're coming to Bootstrap now. In practice, the procedure for estimating the standard error of alpha hat outlined above cannot be applied because for real data, we cannot generate new samples from the original population. However, the Bootstrap approach allows us to use a computer to emulate the process of obtaining new sample sets so that we can estimate the variability of alpha hat without generating additional samples, rather than repeatedly obtaining independent data sets from the population, which we can't do because we don't know the population's sigmas. We instead obtain distinct data sets by repeatedly sampling observations from the original data set. Okay, This approach is illustrated in figure 5.11. 5.11. Okay. So this is the bootstrap. This is the bootstrap where you have your original data set. Okay. That's original data set. And the bootstrap is you select, but you're allowed with repetition. So look. In this one, you've selected observation 3, observation 1, and then observation 3 again. In the second one, observation 2, observation 3, observation 1, etc., until you get this maybe final one, observation 2, observation 2, observation 1. And then you can calculate the alpha for each one of these. How? Well, very easy. Use these three to calculate sigma x squared, these three to calculate sigma y squared, and both of them in conjunction to calculate the covariance, place it in the formula, and that's your alpha. And you do the same for each bootstrap data set. So each one is known as a bootstrap data set. And then we're going to return to 5.10 and compare and see how good the bootstrap is at giving you an actual. Now remember, in real life, you can only perform bootstrap. You won't be able to perform the so-called true because you wouldn't know the underlying distribution. And there's this whole formula over here. And you're going to create B bootstrap data sets. So just very quickly, and this will be the last thing that we do tonight. This approach is illustrated in figure 5.11 on a simple data set, which we call Z, that contains only 3 observations. We randomly select n observations from the data set in order to produce a bootstrap data set, Z asterisk 1. The sampling is performed with replacement. We had repeated observations earlier, which means that the same observation can occur more than once in the bootstrap data set. In this example, Z asterisk 1 contains the third observation twice, the first observation once, and no instances of the second observation. Note that if an observation is contained in Z asterisk 1, then both its x and y values are included. We can use Z asterisk 1 to produce a new bootstrap estimate for alpha, which we call alpha hat asterisk 1. This procedure is repeated b times for some large value of b. And we would normally take, for example, 10,000. Which we call, beg your pardon, in order to produce b different bootstrap datasets from Z asterisk 1 to Z asterisk b. And b corresponding alpha estimates, these over here. We then compute the standard error of these bootstrap estimates using this formula. This serves as an estimate of the standard error of alpha hat estimated from the original data set. And this is now what we create over here. We've done it 1,000 times as well. So we've done from Z asterisk 1 to Z asterisk 1,000. Bootstrapping the 100 observations, assuming that your data set has 100 observations. And this is great. In 5.3, we're now in lab, and that's not going to take us too long, right? So that's probably tomorrow's session. So by midweek, by probably Wednesday, we're going to be on section We're going to be on chapter 6. One final thing, but I probably don't remember how to do it. There is a way of selecting from, is it the sample function? No. Just trying to remember how you select with replacement, but we can do this at a later stage. Just curious. This one's quite so this was quite a short chapter with only around 25 pages, which explains why, and given the double session that we had yesterday, that will explain why we were able to make quite quick work of it. Chapter 6 will be 6 pages, linear model selection and regularization. And we're getting to the fun stuff, because when we do, it's really chapter 8, 9, and 10. And we had mentioned, those will be the last 3 chapters, which are, after that, then we can maybe go on maybe more specific actuarial topics.